Okay, so I'm going to be solving this physics problem. Today, it's a problem that has to do with like a pulley and a brick like attached to it and a rope, and it's pretty much has to do with angular velocity. In this chapter, we've covered angular momentum and a couple different things, but I'll go ahead and get started with the problem. So it says a 45 Newton brick is suspended by a light string from a 2 kilogram pulley. The brick is released from rest and it falls to the floor as the pulley rotates through 5 rads. The pulley may be considered a solid disk of a radius of 1.5 meters. What is the angular speed of the pulley? So here's what we do know about this problem. We have the given information, the 45 newtons for the brick, the how much the pulley weighs, or the mass of the pulley, how much it rotates in rads, and then the radius of that pulley. So we know that velocity is equal to r omega if you're creating the relationship between linear and angular quantities. Then there's the acceleration, linear acceleration, is equal to the radius times alpha. And then the torques, tau equals RF sine of theta equals I alpha. And the moment of inertia of a solid disk is 1/2 mr squared. And alpha is equal to the acceleration over the radius. So let's analyze the diagrams and sum the forces on the brick. So if we sum the forces in the y direction, because the pulley itself is being pulled in the negative direction because of the torque, is equal to the torque sub 1 minus the mass of the brick, right, which is this free body diagram I'm looking at right here, is times gravity, is equal to the negative mass of the brick times the acceleration in the y direction, because it's not moving on the x-axis. So we can solve for the first torque symbolically by setting T1 and manipulating the equation, and we're going to get is equal to the mass of the brick times gravity minus the mass of the brick times the acceleration in the y direction. But we don't have the acceleration yet, so we're going to be able to get to it by plugging in some more information. The sum of the torques on the pulley itself, this is not the brick, it's solving it independently, is equal to the torque on the pulley times the radius times the sine of theta, which is also equal to I alpha that we said previously. Putting this in together and re-manipulating the equation, it's going to come out to be that it's going to equal to be 1/2 times the mass of the pulley times the acceleration of the y direction, which we have the mass of the pulley, but we don't have the acceleration in the y direction. But just to simplify some things, the sine of theta, which is just 1, because the angle between this forces is 90 degrees. So the sine of 90 just equals 1. We mentioned that the moment of inertia of a disk is 1/2 mr squared, and that alpha is the acceleration over the radius. We can get the acceleration a different way, or one of the ways you could get it is if you set the two torques equal to each other. So you're setting the mass of the brick times gravity minus the mass of the brick times the acceleration in the y direction is equal to 1/2 times the mass of the pulley in the acceleration of the y direction. And if you continue to manipulate the equation, it comes out to be, it's going to be 1/2 times the mass of the pulley plus the mass of the brick times the acceleration of the y direction. Now, if you re-manipulate further, you solve this, and you just basically what you're doing is you have to convert some of the units from newtons to kilograms. Otherwise, if you don't, you'll just get the wrong answer. So if you plug all this in and compute it, you're going to get a linear acceleration of 8.05 meters per second squared. And if you convert that to radians, you're using this alpha equals a over the radius, you're going to get 5.36 rads per second squared. So now that we have all of that information, we can go ahead and finish solving this using a motion equation. So we have some other parameters that were given to us in the problem. We know that initially the pulley wasn't moving when the brick fell, right? And that they told us that the pulley rotated 5 rads. So we have that information. And using this to get omega final is equal to the omega initial plus 2 times alpha times the change in the radians, which it told us it rotated 5 degrees, or theta. So if we just do that, plug all in our values and take the square root, we're going to get that the omega final, or the angular velocity or speed, is equal to 7.3 rads per second. And that correlates with the answer that was given. That's it.